Good evening. First of all, it's my privilege to be here, and thank you organizers for giving me an opportunity to present here. And I am Dr. Ramesh Kumar. I am from HPCL Green R&D Center. It is located in East Bangalore, Hoskoten here. And today is my contents is the contents of this presentation is like introduction, why energy storage, how hydrogen energy is stored, nanomaterials for hydrogen storage, and HP Green R&D at hydrogen storage, and future perspective. So in details we can see that sorry. Yeah, this is the data which shift is going on, like we can see that there is a drastic shift in the coal, oil, like it is going in the minus 1.9 and minus 1.5. So in the future, like 2050, there is a decrease in the natural gas and the demand, like oil and coal, it is decreasing. But whereas the hydrogen, bioenergy and electricity is increasing at a CAGR like 2.8, 6.5 is for hydrogen, and bioenergy is at 0.7%. And this is the data like share of renewables. So as we go, like up to 2025, 35, it is drastically it is increasing. So what we can observe is there is a downward trend in the fossil fuels. So we cannot avoid the importing the crude oil, because it's not only useful for the oil and natural gas sector, but also it is useful for the tire rubber industry also. So, and India scenario is like in energy demand doubles by 2047, and oil grows in the same line. Renewable energies will multiply by, and coal declines but in share, but grows in volumes, and biomass trails off to nil. And coming to the introduction, like why after all this one, the renewable energy sources, in renewable energy sources, the hydrogen can replace the existing fossil fuels because of the high calorific value. And on board, like hydrogen storage continues to be challenging because of the, we have to store it at a very, very low temperatures, and very high pressures we need to apply. And advantage of this hydrogen is it is having a high energy density, zero emission fuel, and challenges are like explosive, storage problems, and transportation problems. Types of hydrogen, so there are different types of colors of this hydrogen. So basically, we are trying for the green hydrogen, which we are getting from the electrolysis of water, and targets by US Department of Energy by 2030 is like 10 million metric tons per annum, and 20 MMTPA by 2040. And we know that it is like 111, so $1 per kg by 2031. So India targets 5 MMTPA of green hydrogen by 2030. And regarding the storage, USDOE targets 5.58% by 2025, and ultimate target is 6.58%. So here we can see that how hydrogen can be stored. So if it is in metal hydrides, so we can store it at very low volume. So for a realistic driving distance like 330 miles, so we required 4 kg of the hydrogen. So which occupies the different levels, like only hydrogen if you take, it will occupy like 1 liters of the barrel. And why hydrogen storage? It is useful for the fuel cells and stationary application, more portable application, and transportation, and especially for the vehicles. And sources of hydrogen is like natural gas. At present we are getting like 48%, then oil refineries, oils and coal, then electrolysis. And it is predicted by 2050, like natural gas will be dominate, and oil refineries, it is negligible, and biomass is going to be 8%, and electrolysis we can see up to 22%. and other sources are there. And different types of storage methods are there, physical storage and material storage. So physical storage, which contains compressed gas, cryo or cold compressed liquid hydrogen. So this compressed gas, which requires lot of energy, like we should compress the gas at -253 degrees centigrade, and then it has to be stored in insulated tanks, and we have to minimize the evaporation. So this evaporation is like, if you take a high larger volume, it is saying that Linde, according to Linde, this reports about 4% of the thing is evaporating. So this we need to be the problem we have to rectify here. And in material based, we have different types of materials like absorbent, like MOF, metal organic frameworks, liquid organic like boron nitride methyl cyclopentane, examples like interstitial hydrates, like yesterday we have talked about, we have seen about the interstitial metal hydrates, and chemical hydrogens. And coming to the storage methods, so here we can store the So type 3 and type 4, which basically useful for the storing of compressed hydrogen. So mostly people are using like type 4. So it is having the difference between type 4 and type 5 is type 4, which is having a carbon fabric reinforced plastic, and it can go up to 10,000 psi pressure, and it is having a high capacity when compared to the type 3 cylinders, and it is expensive. Why it is expensive is like it is having a complex of manufacturing process. And in regarding this different types of compressed gas storages, like different types of storage methods, we can see that solid liquid and compressed gas. So storage method, in storage method we can see the cost per unit of the stored energy. So carbon materials, where we can see that very less of less amount, but when compared to the compressed gas, it is taking high cost, and liquid hydrogen it is taking in the medium, and chemical hydrogen it bit high. And the absorption process, which mostly take place in the MOFs. So adsorption and absorption is the two process which will take place. Adsorption is like it is attached. In adsorption, the hydrogen is attached to the surface of a metal either by hydrogen molecules or as an hydrogen atoms. Whereas in absorption, the hydrogen is dissociated into hydrogen atoms, and hydrogen atoms are incorporated in the solid network framework. So because of this weak interactions, it should have like low temperatures we need to go, and high elevated pressures. Like pressure, sometimes we need to go like 300 bars also. So different types of nanomaterials are used for the storage, like carbon based, like CNTs, MOFs, covalent organic frameworks, different and metal hydrides. So coming to the nanomaterials, so nanomaterials it is having a different properties when compared to the bulk. So it is having a very high surface area when compared to the bulk material. Because of this high surface area, the hydrogen diffusion can take place easily, and hydrogen exchange rate will be fast. And coming to the carbon based materials, so in a worldwide, like people are using multi-wall carbon nanotubes. Different types of carbon materials are available, like nano graphite, single wall, multi-wall carbon nanotubes, fullerene, and activated charcoal. So what here is like hydrogen molecules which is having a 0.8 nanometers of diameter, which will diffuse into the carbon nanotubes. Thereby absorption will take place easily. And coming to the data, like activated charcoal can be modified to get more hydrogen uptake. So we can treat with KOH, or we can dope with platinum, palladium. So CNTs which are doped with lithium, which are having a hydrogen capability up to 20 weight percentage. So which is having high, because lithium is high absorption capacity for the hydrogen. and different types of materials they are using, like, multi-wall carbon nanotubes, and which are doped with different metals. So copper, cobalt, iron, nickel, palladium. So CNF is carbon nanofibers, which can also be useful for the storage. And coming to the MOFs, so why people are using the MOF is, so advantages are like, for the MOFs, it can have low density and high specific surface area, tunable porous structures. So basically, we can tune the structure by using the different types of organic molecules, like we can use the sulfonates, imidazole, tetrazonate, tetraimidazoles. So different types of organic molecules we can use, and also exposed to the metal nodes. So we can use the copper, zinc, nickel. So different types of metals we can use, so that we can play the better hydrogen uptake capacity, and it can be very easily reproducible, and fissile synthesis we can easily prepare at ambient temperatures also, and it is a controllable chemical functionality, and it can be easily feasible scale up also. So different types of MOFs, like MOFs 5. So in this one we can see that if you see here, like storage conditions, so pointer, okay. So if you see here, like, depend upon the temperature and pressure, the hydrogen capability will drastically change. So if we store at low temperature, like MOF 393, if you see, like, it is storing at temperature at 77 Kelvin and 56 bar. So it is giving an hydrogen capacity like 9.02. Whereas if you do at the same thing at room temperature and at 140 pressure, it is absorbing only 0.46. So for the 76 Kelvin, so we need to apply lot of energy. So what we have to do is, like, we need to store the energy at low at room temperatures and at low pressure condition, so that it will be commercially viable, and the cost of the hydrogen storage we can come down. It will be come down. And metal hydrates for the hydrogen storage, like different types of metal hydrates we can use. And to improve those metal hydrates, we can dope with some other metals, and we can mix with some other materials like titanium, or porous carbons or non-porous carbons, so that the hydrogen uptake capacity will improve. And coming to the hydrogen storage technologies, we have, like, compressed hydrogen storage, advantage and disadvantage we can see. So what HPCL is doing at, like, what HPCL is doing in hydrogen storage is, we have synthesized MOFs, and which is at we have succeeded at around 1 weight percentage of the uptake, and at room temperature, and at very 77 bar, and around 1%, and that is a core shell method, and that is we are going to be patented, that one. And future perspective is, like, long-term reliable policies have adopted to encourage the novel technologies and advanced hydrogen production, purification, and storage. We have storage technologies to be come out, and improved and low priced electrolysis methods have to be improved. So entire industry, like hydrogen industry, so there is a integration and coordination with oil and natural gases to be needed. So this is from my team. Thank you.